October 1974, Las Vegas, Nevada. The engineering consensus from European mining equipment manufacturers would never fully capture what they witnessed at the American Mining Congress that morning. A massive haul truck that defied everything established mining engineering said was physically possible for surface operations. Through the convention center lights and industrial displays, the General Motors Terex Titan stood 66 feet long and 22 feet tall, with specifications that seemed impossible to European observers. No complex transmissions, no torque converters, no electronic weight restrictions. Yet it promised to haul 350 tons using locomotive technology that European truck designs had never imagined possible. In European factories, mining engineers calculated that ground pressure would crush road surfaces, that no tire could handle such weight, that mechanical stress would destroy any truck attempting such capacity. Each existing haul truck was essentially limited to 150 tons, different engineering approaches, different power systems, different operational restrictions. Most required careful load management and sophisticated mechanical systems. The Americans were operating with engineering philosophy the Europeans had never considered viable: diesel locomotive engine, electric drive motors, mechanical simplicity without computer oversight, hauling capacity that doubled existing truck limitations through raw electrical power delivered exactly where needed. 8,000 miles from European engineering workshops, the most decisive mining truck revolution in industrial history was revealing itself. Not in sophisticated electronics, not in computer-controlled optimization, but in the mechanical reliability that connected locomotive power to mining operations in ways European engineering traditions never imagined possible. By 1969, mining engineers across 3 continents had reached the same frustrating conclusion. The mathematics were unforgiving. Ore grades were dropping steadily worldwide, which meant hauling exponentially more waste rock to reach the same quantity of valuable minerals. Every major mining operation faced the same brutal economics: more tonnage, longer hauls, deeper pits. The largest haul trucks in existence could barely manage 150 tons per load, and that capacity represented the absolute engineering ceiling according to every calculation European manufacturers had performed. The fundamental problem wasn't just size, it was physics. Ground pressure calculations showed that any truck exceeding 200 tons would crush standard mining road surfaces. Tire technology couldn't handle the contact pressure. Mechanical transmissions would shatter under the torque requirements. Drive axles would snap. Suspension systems would fail catastrophically. The European engineering consensus was mathematically precise and operationally proven. 150 tons was an impossible target that violated every known principle of heavy equipment design. General Motors Terex division engineers gathered in their Warren, Michigan facility with a completely different perspective. Instead of accepting the limitations that defined traditional truck engineering, they asked a single revolutionary question. What if mining trucks didn't have to think like trucks at all? What if they could think like locomotives instead? The concept emerged from studying railroad operations where massive diesel engines routinely pulled thousands of tons across continental distances without the mechanical complexity that plagued mining trucks. The breakthrough insight centered on power delivery systems. Traditional mining trucks used mechanical transmissions that converted engine power through complex gear trains, torque converters, and drive shafts. Every component in that mechanical chain represented a potential failure point under extreme loads. Locomotives solved the same power delivery problem through elegant simplicity. Diesel engines drove electrical generators, which powered electric motors directly connected to the wheels. No transmissions, no torque converters, no complex mechanical linkages between power generation and power application. General Motors possessed a crucial advantage that no other manufacturer could match. Their electromotive division had been building locomotive engines for decades, perfecting diesel power plants that delivered constant horsepower output regardless of load conditions. The EMD 16645 E4 engine represented the pinnacle of locomotive engineering. 16 cylinders, 3,300 horsepower, 10,320 cubic inches of displacement. Each cylinder displaced more volume than an entire automobile engine, with bore and stroke dimensions that dwarfed truck engine specifications. The Terex engineering team realized that locomotive engines operated under fundamentally different design parameters than truck engines. Truck engines were designed for varying loads and operating conditions, with power curves that fluctuated based on speed, terrain, and payload. Locomotive engines were engineered for consistent power delivery under constant load conditions. They maintained rated horsepower output, whether pulling empty cars or fully loaded freight trains across mountain passes. This constant power characteristic was exactly what mining operations required for hauling massive loads up steep pit ramps. The electrical drive system offered additional advantages that mechanical transmissions couldn't match. Electric motors delivered maximum torque from 0 RPM, providing instant pulling power without the complex gear ratios that mechanical systems required. Speed control was infinitely variable through electrical regulation rather than discrete gear selections. Most importantly, electrical systems could handle the massive torque requirements without the mechanical stress that destroyed traditional transmissions under extreme loads. General Motors committed to proving their locomotive-based concept through the most ambitious mining truck project ever attempted. The specifications were staggering by any measure: 350-ton payload capacity, gross vehicle weight exceeding 1,200,000 pounds, overall length of 66 feet. The truck would be longer than a railroad car and taller than a two-story building. Every component would need to be engineered from scratch, since no existing truck parts could handle the operational requirements. The economic projections were equally intimidating. General Motors estimated that production versions of the Titan would cost approximately $1.5 million in 1976 pricing, roughly $6.5 million in today's currency. That represented 5 times the cost of existing mining trucks, placing the Titan in an entirely different economic category. Mining companies would need to justify the investment through dramatically improved productivity, longer operational life, or reduced operating costs per ton moved. European manufacturers responded to General Motors' announcement with professional skepticism, backed by decades of engineering experience. Tire manufacturers stated categorically that no tire technology could support the ground pressure generated by a 600-ton vehicle. Road construction experts calculated that standard mining surfaces would require complete reconstruction to handle such weight concentrations. Mechanical engineers pointed out that the proposed specifications violated fundamental principles of automotive design that had governed heavy equipment development since the early 20th century. The criticism extended beyond technical concerns to philosophical disagreements about American versus European engineering approaches. European manufacturers traditionally emphasized incremental improvements to proven designs, refining existing technology through careful engineering and extensive testing. The American approach represented by General Motors appeared reckless, a brute force solution that ignored established limitations rather than systematically addressing them through sophisticated engineering. General Motors understood that their locomotive-based concept would succeed or fail based on real-world performance rather than theoretical calculations. The Titan project represented more than an engineering experiment. It was a fundamental bet on American mechanical engineering philosophy. If locomotive technology could be successfully adapted to mining applications, it would revolutionize surface mining operations worldwide. If the project failed, it would validate every European expert who claimed that 350-ton capacity was engineering fantasy rather than achievable reality. The massive assembly hall at General Motors' Diesel Division in London, Ontario echoed with the sound of locomotive-scale construction throughout 1973. Workers accustomed to building railroad engines found themselves applying familiar techniques to an entirely unprecedented project. The Terex Titan emerged piece by piece, each component requiring custom fabrication, since no existing mining truck parts could handle the operational demands. The locomotive engine that would power this mechanical giant arrived from Electromotive Division as a complete 16-cylinder powerhouse, but everything else demanded original engineering solutions. The chassis construction revealed the true scale of the undertaking. Traditional mining trucks used modified automotive frames that could be manufactured using standard heavy equipment techniques. The Titan required a structural foundation equivalent to a railroad car, with steel members thick enough to distribute 600 tons across the wheelbase without flexing. Welders worked with steel plates measured in inches rather than fractions, creating joints that could handle stresses no truck frame had ever experienced. The completed chassis stretched 66 feet from front to rear, longer than most mining buildings, and requiring custom transportation arrangements for movement between assembly stations. Tire technology represented perhaps the most challenging engineering obstacle. Existing mining truck tires were designed for maximum loads of 75 tons per tire, but the Titan would require tires capable of supporting over 150 tons each. No tire manufacturer had attempted such specifications, partly because no application had ever demanded such capacity. The engineering team worked directly with tire manufacturers to develop custom compounds and construction techniques that could handle the ground pressure without catastrophic failure. The final tire specifications called for diameters exceeding 12 feet, with sidewall construction strong enough to support a loaded freight car. The electrical system installation demonstrated the fundamental difference between locomotive and truck engineering approaches. Traditional mining trucks use 12-volt electrical systems similar to automobiles, with relatively simple wiring harnesses and basic instrumentation. The Titan required electrical generation and distribution systems equivalent to a small power plant. The electromotive alternator produced enough electricity to power a neighborhood, feeding current through cables thick enough to serve industrial facilities. Electric drive motors at each rear wheel weighed more than entire automobile engines, delivering torque through reduction gearing that could multiply the motor output by ratios impossible with mechanical transmissions. Assembly workers quickly learned that locomotive engineering operated by entirely different standards than automotive manufacturing. Every bolt was larger, every connection was heavier, every component was built for decades of operation under extreme conditions rather than the replacement cycles that governed truck manufacturing. The fuel system alone required industrial-scale components, tanks holding 800 gallons of diesel fuel, pumps capable of delivering locomotive-level fuel flow, and filtration systems designed to handle the massive consumption of a 3,300 horsepower engine running continuously under full load. The completed Titan rolled out of the London facility in early 1974 as the largest mobile land vehicle ever constructed. Its dimensions defied conventional understanding of truck proportions: 22 feet tall, 31 feet wide, with a turning radius that required specially designed maneuvering areas. The gross vehicle weight of 1,200,000 pounds placed it in a category occupied only by locomotives and industrial machinery, far exceeding any road-legal vehicle specifications. Even empty, the Titan weighed more than most loaded mining trucks. General Motors unveiled their mechanical giant at the American Mining Congress in Las Vegas during October 1974, where it dominated the convention center floor like nothing the mining industry had ever witnessed. Convention attendees walked beneath the massive chassis, studying the locomotive engine installation and electrical drive components that represented a completely different approach to mobile mining equipment. The Titan attracted crowds not just for its size, but for the engineering philosophy it embodied. Raw mechanical power delivered through proven locomotive technology rather than the increasingly complex systems that characterized modern truck design. The specifications that General Motors presented to potential customers demonstrated the locomotive approach in concrete terms. The EMD 16645 E4 engine delivered 3,300 horsepower continuously, regardless of load conditions or operating environment. Traditional truck engines varied their power output based on speed, load, and operating conditions, but locomotive engines maintained rated horsepower across their entire operating range. This constant power characteristic meant that the Titan could maintain consistent performance whether climbing steep pit ramps or hauling loads across level terrain. The electrical drive system provided additional capabilities that mechanical transmissions couldn't match. Electric motors delivered maximum torque from standstill, eliminating the need for complex gear ratios and torque multiplication systems. Speed control was infinitely variable through electrical regulation, allowing precise speed matching for loading operations or fuel-efficient highway travel. Most importantly, the electrical system could handle overload conditions that would destroy mechanical components, since electric motors could briefly deliver torque levels far exceeding their continuous ratings. Mining industry reaction mixed fascination with skepticism as engineers examined the Titan's revolutionary specifications. The locomotive engine approach clearly solved power delivery problems that had limited truck capacity for decades, but the economic implications were staggering. The projected cost of $1.5 million represented 5 times the investment required for conventional mining trucks. Mining companies would need to justify the expense through dramatically improved productivity, reduced operating costs, or extended service life that conventional equipment couldn't provide. The Titan represented not just a larger truck, but an entirely different economic category of mining equipment that would require fundamental changes in operational planning and capital investment strategies. The engineering proof was complete, but the real test lay ahead in actual mining conditions, where theoretical calculations would meet the unforgiving demands of continuous heavy-duty operation. Kaiser Steel's Eagle Mountain iron mine in California provided the perfect proving ground for General Motors' revolutionary concept, but the initial results in January 1975 revealed both the promise and the problems of locomotive-scale mining equipment. The Titan arrived at the desert facility like a mechanical dinosaur, dwarfing every piece of equipment on the site and requiring immediate modifications to loading areas, maintenance bays, and haul roads that had never accommodated anything approaching its dimensions or weight. Mine operators quickly discovered that the Titan's locomotive engine delivered exactly the constant power that General Motors had promised, but the mechanical system surrounding that engine required continuous attention that conventional trucks never demanded. The massive diesel power plant ran with railroad-like reliability, maintaining 3,300 horsepower output whether climbing steep pit ramps or traveling across level terrain. However, the custom-built components that connected locomotive technology to mining truck operations, the electrical generators, drive motors, steering systems, and hydraulic circuits, suffered frequent failures that interrupted operations and frustrated maintenance crews. The learning curve was steep and expensive. Maintenance technicians accustomed to working on 150-ton trucks found themselves dealing with components that weighed as much as entire conventional vehicles. Tire changes required industrial cranes rather than standard garage equipment. Electrical troubleshooting involved systems that generated enough current to power small towns. Even routine maintenance tasks like oil changes demanded specialized equipment and procedures that most mining operations had never needed to develop. Despite these operational challenges, the Titan consistently demonstrated capabilities that vindicated General Motors' engineering approach. The locomotive-style electrical drive system provided precise speed control and maximum torque at all operating speeds, allowing operators to maintain consistent productivity regardless of load conditions or terrain variations. The massive payload capacity meant fewer trips to move equivalent tonnage, reducing fuel consumption per ton hauled, and increasing overall operational efficiency when the truck was actually running. The mechanical philosophy that General Motors had embedded in the Titan's design proved its worth during breakdown situations. When conventional trucks experienced transmission failures or engine problems, the complex interactions between electronic systems often created diagnostic nightmares that required specialized technicians and computer equipment. The Titan's mechanical simplicity meant that failures were usually straightforward problems that mining mechanics could understand and repair using conventional tools and techniques. A failed electric motor could be isolated and bypassed. A hydraulic leak could be traced and fixed without affecting the locomotive engine or electrical generation systems. Over 4 years of operation at Eagle Mountain, the Titan hauled approximately 3.5 million tons of iron ore and waste rock, proving that locomotive technology could be successfully adapted to mining applications. The tonnage figures represented real productivity gains that demonstrated the economic potential of the locomotive approach, despite the frequent maintenance interruptions that plagued the early operational period. Mining engineers began to understand that the Titan's capabilities extended beyond simple payload capacity to include operational advantages that conventional trucks couldn't provide. The transition to Sparwood, British Columbia in late 1978 marked a turning point in the Titan's operational history. Kaiser Steel's coal mining operation in the Canadian Rockies provided different challenges and opportunities than the California iron mine. The terrain was more demanding, with steeper grades and harsher weather conditions. But the coal mining operation had maintenance facilities and operational expertise better suited to handling the Titan's unique requirements. Westar Mining's acquisition of the Sparwood operation in 1983 brought new management perspective to the Titan's capabilities. Rather than viewing the massive truck as an experimental prototype, Westar's engineers approached it as proven technology that required proper operational procedures rather than fundamental design changes. The company's decision to purchase the Titan from General Motors for $200,000 plus $1 million in spare parts demonstrated confidence in the locomotive-based concept that previous operators had struggled to achieve. The key breakthrough came from understanding how to operate the Titan at its mechanical limits rather than within conservative electronic parameters. Westar's maintenance teams developed procedures that maximize the truck's uptime by treating it as industrial equipment rather than oversized automotive machinery. They established maintenance schedules based on locomotive practices rather than truck service intervals, recognizing that the EMD engine and electrical systems require different care than conventional mining equipment. The results vindicated everything General Motors had claimed about locomotive technology in mining applications. Under Westar's management, the Titan achieved uptime rates exceeding 70% while regularly hauling loads that exceeded its 350-ton rating. The truck was literally carrying more weight than its design specifications, something that modern electronic systems would never permit, but that the mechanical design could handle without difficulty. The operational philosophy that emerged from Westar's experience highlighted the fundamental difference between mechanical and electronic approaches to equipment management. The Titan's locomotive engine maintained constant power output regardless of load conditions, while the electrical drive system delivered precise torque control without the complex gear ratios that limited conventional trucks. This mechanical robustness allowed operators to push the equipment to its actual physical limits, rather than the conservative parameters that electronic systems imposed. Most significantly, the Titan's success at Sparwood demonstrated that American mechanical engineering could solve problems through straightforward power application rather than sophisticated control systems. The truck hauled more tons per trip, operated reliably under extreme conditions, and maintained productivity levels that conventional equipment couldn't match. The locomotive approach had proven itself in the most demanding mining conditions, establishing a foundation for understanding why mechanical simplicity often outperformed electronic complexity in heavy industrial applications. The worldwide coal market began its precipitous decline in the late 1970s, fundamentally altering the economic landscape that had made the Titan project viable. Mining companies that had been expanding operations and investing in larger equipment suddenly found themselves cutting production, laying off workers, and canceling capital expenditure programs. The projected market for ultra-large haul trucks that General Motors had identified simply evaporated as coal demand dropped, and mining operations focused on maximizing efficiency from existing equipment rather than purchasing revolutionary new machinery. More troubling for General Motors was the simultaneous emergence of electronic control systems that promised to revolutionize mining truck operations through computer-managed efficiency rather than raw mechanical power. Competing manufacturers were developing sophisticated load monitoring systems, automatic transmission controls, and computerized diagnostic capabilities that mining companies increasingly demanded as standard equipment. The industry was shifting toward electronic optimization rather than mechanical simplicity, viewing computers as the solution to operational problems that had historically been solved through larger, more powerful equipment. The philosophical divide between mechanical and electronic approaches became apparent in every major mining equipment purchase decision. Mining companies were beginning to favor trucks that could prevent operators from exceeding design parameters, rather than trucks that could mechanically handle whatever loads operators demanded. Electronic systems promised to protect expensive equipment from damage, optimize fuel consumption through algorithmic controls, and provide detailed operational data that manual systems couldn't deliver. Caterpillar emerged as the leader in this electronic revolution, developing sophisticated control systems that monitored every aspect of truck operation in real time. Their engineers argued that computer-controlled transmissions could deliver power more efficiently than mechanical systems, that electronic load monitoring could prevent the equipment damage that reduced operational life, and that automated systems could achieve consistency that human operators couldn't match. The mining industry embraced this technological sophistication as the obvious evolution beyond the crude mechanical approaches that had characterized earlier equipment generations. The Titan's mechanical philosophy suddenly appeared outdated rather than revolutionary. While General Motors had proven that locomotive technology could deliver massive hauling capacity and operational reliability, the industry was moving toward equipment that prioritized electronic intelligence over raw mechanical capability. Mining companies wanted trucks that could communicate with central dispatch systems, monitor their own performance parameters, and automatically adjust operations to maximize efficiency within predetermined safety limits. General Motors faced the harsh reality that engineering excellence didn't guarantee market success. The Titan represented superior mechanical engineering and proven operational capability, but the mining industry was demanding electronic features that the locomotive-based design couldn't provide. Retrofitting sophisticated computer systems onto the mechanically simple Titan would have compromised the very advantages that made it effective, while developing an entirely new electronic version would have required abandoning the locomotive technology that was the truck's fundamental strength. The economics became inescapable as mining companies consistently chose smaller, more sophisticated trucks over the Titan's massive capacity. Electronic systems added relatively modest costs to conventional trucks while providing features that mining operations increasingly considered essential. The Titan's locomotive, engine and electrical drive system delivered superior performance, but at a price premium that mining companies were unwilling to pay when electronic alternatives promised similar productivity improvements at much lower capital costs. Competition intensified as European manufacturers introduced their own ultra-large trucks that combined significant payload increases with the electronic systems that American mining companies demanded. These trucks couldn't match the Titan's 350-ton capacity, but they offered 250 to 300-ton payloads with computer-controlled transmissions, electronic load monitoring, and automated safety systems. Mining companies viewed these trucks as the optimal combination of increased capacity and modern technology, making the Titan's mechanical approach appear primitive by comparison. The final blow came when Caterpillar announced development of the 797 series, promising payload capacities that would exceed the Titan while incorporating the most advanced electronic control systems ever applied to mining equipment. The 797 represented everything the mining industry wanted: massive hauling capacity combined with sophisticated computer management that would optimize every aspect of operation. Caterpillar's announcement effectively ended any remaining market interest in the Titan's mechanical approach. General Motors made the inevitable decision to cancel Titan production before manufacturing the first commercial unit. The prototype had proven that locomotive technology could be successfully adapted to mining applications, but the market had moved beyond valuing pure mechanical capability. Mining companies wanted electronic intelligence, computerized efficiency, and automated optimization rather than the straightforward mechanical power that the Titan delivered so effectively. The irony was profound. At the exact moment when the Titan was achieving its greatest operational success at the Sparwood mine, hauling loads exceeding its design capacity with uptime rates that conventional trucks couldn't match, the mining industry was embracing electronic systems that would prevent trucks from operating at their mechanical limits. The locomotive approach that General Motors had developed was proving its superiority in actual mining conditions, while the market was choosing electronic alternatives that prioritized theoretical optimization over practical performance. The Titan's failure to reach production represented more than a business disappointment for General Motors. It marked the end of an engineering era that valued mechanical solutions over electronic complexity, operational capability over theoretical efficiency, and proven performance over sophisticated control systems. The mining industry was choosing a fundamentally different path toward equipment improvement, one that would rely on computers to manage operations that had previously been controlled by mechanical systems and human operators. The prototype would continue operating at Sparwood for another decade, hauling millions of tons while demonstrating daily that mechanical engineering could deliver results that electronic systems couldn't match. But the market had already decided that the future belonged to computers rather than locomotives, regardless of which approach actually moved more tons more reliably. the Caterpillar 797 that finally entered service in September. 1998 represented the complete triumph of electronic philosophy over mechanical engineering. With a 360-ton payload capacity that technically exceeded the Titan's specifications, the CAT 797 embodied everything the mining industry had demanded: sophisticated computer controls, electronic load monitoring systems, and automated safety protocols that prevented operators from exceeding predetermined parameters. Yet this electronic sophistication came with operational restrictions that the mechanical Titan had never imposed on its operators. The Vehicle Information Management System that Caterpillar installed in the 797 exemplified the electronic approach to mining truck operation. The VIMs constantly monitored payload weight, engine parameters, transmission temperature, and dozens of other variables, using algorithms to determine optimal operating conditions for each specific situation. When the system detected overload conditions, it automatically limited engine power, restricted transmission gear selection, and reduced maximum operating speed until the load was reduced to acceptable levels. The computer would not permit the truck to operate at its mechanical capacity if electronic calculations suggested potential equipment damage. Modern mining operations accepted these electronic limitations as necessary trade-offs for equipment longevity and operational efficiency. The VIMs provided detailed data logging that allowed mining engineers to optimize haul routes, schedule preventive maintenance, and track productivity metrics that mechanical systems couldn't deliver. Electronic controls prevented the operator errors that could damage expensive components, while automated systems reduced fuel consumption through precise engine management that human operators couldn't match. The sophistication was impressive, but it came at the cost of operational flexibility that mechanical systems had provided. The fundamental limitation of electronic systems became apparent in practical mining operations, where conditions exceeded the parameters that computer programmers had anticipated. The 797's payload monitoring system was accurate only to within 20% due to mechanical variables like suspension strut friction, hydraulic pressure variations, and frame flex that electronic sensors couldn't perfectly compensate for. When these measurement uncertainties triggered safety protocols, the truck's computer would impose operational restrictions even when the mechanical systems could handle higher loads without difficulty. The electronic speed management system created additional operational constraints that the Titan had never experienced. The CAT 797's computer monitored dozens of variables to calculate safe operating speeds for different load conditions, automatically limiting engine RPM and transmission gear selection when algorithms determined that conditions were approaching safety thresholds. This electronic oversight prevented operators from pushing the equipment to its mechanical limits, even when those limits were well within the truck's actual capability. The computer prioritized theoretical safety margins over practical operational requirements. In contrast, the Titan's mechanical controls had allowed operators to utilize the full capability of the locomotive engine and electrical drive system without electronic interference. The EMD 16645E4 engine delivered its full 3,300 horsepower whenever the operator demanded it, regardless of load conditions or computer calculations about optimal efficiency. The electrical drive motors provided maximum torque at any speed the operator selected, without algorithmic limitations or safety overrides. If the mechanical systems could handle the load, the truck would haul it. The operational philosophy difference became most apparent in overload situations that routinely occurred in actual mining conditions. Modern electronic trucks like the 797 would detect overload conditions and automatically restrict performance until the load was reduced to computer-approved levels. The VIM system would log warnings, limit transmission to second gear, reduce maximum engine RPM to 1750, and activate automatic retarder speed restrictions until the excess weight was removed. These electronic safeguards protected the equipment but prevented it from working at its actual mechanical capacity. The Titan's approach to overload situations was refreshingly direct. If the locomotive engine could generate sufficient power, the electrical system could deliver the torque, and the mechanical components could support the weight, the truck would complete the haul. During its years of operation at Sparwood, Westar Mining regularly loaded the Titan beyond its 350-ton rating because the mechanical systems could handle the additional weight without difficulty. No computer override prevented this practice, No electronic system logged complaints, and no automatic controls reduced performance based on theoretical calculations. The fuel consumption comparison revealed another aspect of the mechanical versus electronic philosophy divide. The Titan consumed 265 liters per hour, a massive fuel requirement that powered the 3,300 horsepower locomotive engine under all operating conditions. Modern electronic trucks achieved better fuel efficiency through computer-controlled engine management that optimized power output for specific load and terrain conditions. However, this electronic optimization often came at the cost of available power when conditions demanded maximum performance. The reliability comparison was equally instructive. Electronic systems in modern trucks provided sophisticated diagnostic capabilities that could identify potential problems before they caused failures, allowing preventive maintenance that reduced unexpected downtime. However, the electronic systems themselves became additional failure points that could disable trucks even when mechanical components were functioning properly. Computer malfunctions, sensor failures, and software glitches could shut down perfectly capable mechanical systems, creating new categories of operational problems that purely mechanical trucks had never experienced. After 17 years of continuous operation, Westar Mining retired the Titan from active service in 1991, not because it could no longer perform its hauling mission, but because the mining industry had moved entirely to electronic systems that provided operational data and control capabilities that the mechanical Titan couldn't match. The locomotive-based truck had proven that mechanical engineering could deliver sustained performance that exceeded design specifications, but the industry valued electronic sophistication over raw mechanical capability. The final irony was undeniable. The 1973 Titan could haul 350 tons every single trip for 17 years without electronic restrictions, while modern 400-ton trucks required computer approval to carry their rated loads. The mechanical approach had delivered exactly what General Motors had promised: locomotive power adapted to mining applications, providing reliable transportation for massive loads without the operational limitations that electronic systems imposed. Sometimes the most sophisticated solution was simply the most reliable solution.